I'm Seok Choi from South Korea. Today I will present a talk about API Deobfuscator, how to resolve obfuscated API functions in modern Packers. Why API deobfuscation matters? Malwares hide functionalities by API obfuscation. Malware writers use commercial packers such as Damida or Frame Protect to obfuscate their APIs. And some malware writers use their own obfuscation techniques. They even develop their own custom obfuscators. And so far, there is no deobfuscation tools for modern Packers. I mean, the modern with latest version. For example, regarding Damida, when we search for Damida unpacker on Google, then we can find some articles how to deobfuscate and some YouTube videos, the technical details, but they work just on previous versions of Damida. The latest version is 2.3.5, but the information that internet gives us how to unpack Damida 2.1 and so on. And there is no x64 unpackers. So I wanted to deobfuscate it, such latest version packed binary files. And I will talk three things. First, API obfuscation techniques. The second, how to deobfuscate it, such the API obfuscation technique. And I will show you some implementation and demo. Modern Packers use various obfuscation techniques. They use anti-debugging, for example, VM detection, debugger detection, anti-disassembly, anti-tampering, anti-debugger attach, and they often use virtualization obfuscation to lengthen the dynamic instruction trace, and they use polymorphism and metamorphism, that is opposite to code optimization. They lengthen by inserting garbage instructions and API obfuscation. Today's talk focuses on API obfuscation. And API obfuscation techniques can be classified into two. The first is static API obfuscation, that obfuscation techniques are only used compile time, that is packing time. And the second is dynamic API obfuscation. In dynamic API obfuscation, packed executable file contains some runtime obfuscator, and that expands API code, API function code into some memory area. And you can find more API obfuscation techniques on our Museum of API Obfuscation on Win32 of Symantec. In static API obfuscation, API functions are obfuscated compile. There is packing time. It is obfuscated just once, and when we load the binary with debugger, the code is always the same, so it is relatively easy to analyze static API obfuscated binaries. Function instructions and addresses are the same with each execution, although the addresses are moving because of ASLR. In the picture, you can see how API obfuscation is applied. At original entry point, that is, when we unpacked, partly, then we can find original API call is obfuscated into the instruction itself, call function address is obfuscated, so it redirects to other section of the binary. There are obfuscated caller code, and the obfuscated caller code resolve the obfuscated address or doing something different, and finally they go to API function code. But some binaries also obfuscate API function, parallel API function code. So here is an example. I made a binary tracer and executed Damida 2.3.3 packed binary files. Yeah, I packed my own easiest sample code on address 1017. There is a call instruction to another section of the obfuscated file, and there are hundreds of instructions, but most of them are garbage, and they branch into other section, and at last API call is performed by return instruction. The last return instruction directs the control flow to API function code. And for VM Protect, they use return. Their address is not the top of the stack. The return address is somewhere in the stack. In dynamic API obfuscation, API functions are obfuscated during runtime while unpacking. Both API call instruction and API function code are obfuscated. So call API function address can be obfuscated sometimes and not obfuscated in Damida 64 bits. And API function code itself is obfuscated runtime. So when the obfuscated API function address is called, it is directed, the control flow is directed to obfuscated API function code address. That is runtime allocated memory area. And here is another example. I packed this Damida 64 bits. The first instruction in the picture calls to another area. Newly allocated area don't have names, and execute some instructions, hundreds of instructions, and at last they call something, and they don't even call the API function itself, because whole API functions are obfuscated, but they don't obfuscate the API function call inside the obfuscated code. So we can sometimes we can check, set breakpoints on some other point of API function that is called inside the obfuscated API called API functions. Then how we can obfuscate API functions in modern packers. In this research, I didn't mean to develop some unpack or dumping some that is executable. I just wanted to analyze the executable file by debuggers and disassemblers and decompilers. And so after the obfuscation, we have original entry point. That is used for debuggers and disassemblers. And I want to recover API function calls at original entry point. Finding original entry point is somewhat easy. In 2006, Paul Royal wrote some paper called Poly Unpack. He opened his tool online, so we can use it, but it's very slow. And so I developed my my own tools to find original entry point. It records every memory write and execute. And yeah, when I first developed this tool, it took so long because it saved every written memory addresses. So I decided to save memory address per blocks to save memory. And OEP is the last written address that is executed. And after we find OEP, we can resolve API functions. For static API obfuscation, I suggest iterate run until API method. There is some function pre-run analysis. And for dynamic API obfuscation, I suggest memory access analysis. So for static obfuscators, that include the MIDA 634 and VM Protect 32 and 634. And yeah, some other packers and custom packers still use static obfuscation techniques. So first we need to find API call candidates at OEP. I use call patterns. In 64-bit binary, call keyword pointer to something is changed into call relative 32 when obfuscated. So yeah, this is different from packers. So we need some prior knowledge on packers. But yeah, we first find obfuscated caller instructions. Yeah, that is this. Yeah, we can find at OEP with debugger. Yeah, when we search for intermodular calls in debugger, we can find obfuscated calls that doesn't have any name. And I did it with Intel pin, search obfuscated call by pattern. Yeah. Call relative 32 is a candidate. And check whether the address is in another section of the process image. And we need to check the call target is disassembled correctly, because the call target address is approximation. We have redundant addresses, so we need to check the call target is disassembled correctly. And finally, when we run the call instruction, obfuscated call instruction, then the execution path go into API function code. So if we execute call obfuscated caller, then obfuscated caller code is executed, and finally API function code is executed. So we can use some static analysis or symbolic execution techniques to resolve these calls, but it's somewhat hard and error prone. So I decided to use some debugger techniques. So I changed for 64 bits RIP and EIP in 32 bits is change it into candidate API call addresses and just execute it until API function. So the first call instruction is executed, and it branches into other section of the code, and finally it goes to the API function code. And we need integrated check again, because we use approximated candidate address. So I check stack pointer and check the stack itself, whether it is changed and do run until API again and again until we check all API call candidates. So at last, we have the call addresses and target API columns. Iterative run until API method can be applied to various packers. You can unpack VM protect, Dummy.64. In VMP, API function call is virtualization obfuscated, so it's lengthy. The execution trace is lengthy. And Dummy.64, it is not so lengthy as VM protect. It is just mutated. And in Obsidian Packer, it is a little bit strange, but it obfuscated the call instruction itself and also the first few instructions in an API function. So in Obsidian packed binaries, the execution path go one of the API function code. And sometimes I analyze custom packer packed binaries. They use some tricky method to obfuscate the API function. For example, they use some encoding and decoding of the API function using strings. But sometimes they use their key with some runtime generated key. So it is difficult in such cases. But eventually, execution is redirected into a real API function. So we can debug x64 binary with, I use x64 debugger after the obfuscation. And every addresses are resolved to real API function. And it is running, and we can dump with some execution dumpers, and we can use IDA Pro, and even it is decompiled, and IAT is recovered. And the second is API deobfuscation for dynamic obfuscators. It's a little bit complex than static API obfuscation. In dynamic obfuscation process, we can observe that every API functions are deobfuscated one by one. So runtime obfuscator embedded in the binary itself reads each function and obfuscated each instruction and writes the obfuscated code into a newly allocated memory. And each function is obfuscated in sequence. In this picture, I put some means of bind. When we look at the execution trace, we can find some bind function instructions are read, and the instruction is expanded to other area, and it is written. And next, bind and connect. It is done alphabetically. So instead of doing some analysis, I decided to use the memory access pattern. So memory access analysis relates memory reads on API function code and corresponding memory writes on obfuscated code. That is, instruction addresses of obfuscated API function is mapped into original API function. Then, after constructing a map, then we can recover original API function by the obfuscated call target addresses. So we first need to construct a map from obfuscated address to API function. In this picture, write addresses before next API function reads, its approximation is bigger than obfuscated function instruction addresses. So obfuscated function instruction addresses are read and written. There are some garbage writes. So it is contained. Yeah, it is contained. Read addresses are contained in write address, and obfuscated API call target address is contained in read addresses. So we need to record every memory writes before the next API function or DLL reads. And regarding reads, I need to check the memory read addresses is contained in some API addresses. And I limited the number of memory writes for the last API function. And we need to identify obfuscated call at OEP. I did it also by pattern matching. Matched patterns may contain false positives. Yeah. And after target address resolution, misinterpreted instructions disappears by checking. And there are direct call and indirect call, so we need other things each. Direct call resolution is done. If the call targets are in the constructed map from obfuscated address to API function, we need to modify call targets to the original API function address. And regarding indirect call, because original segments .text and .idata that contains input address table are merged into one segment when the binary is packed, we need to identify a memory block that contains successive obfuscated API function addresses. The memory area is at first all zeros in Domidar, or some garbage code in burn protect. And we check it, whether it was meaningless before and it contains some input addresses. It is a heuristic, so we need to improve. And at OEP, we need to modify obfuscated call addresses in the IAT candidate with the original API function. So after doing this, we can debug x86 binary with only debugger after deobfuscation. And we can dump it to executable file and decompile and disassemble, do static analysis. And I want to show two demos. I prepared two packed samples. It takes a long time. First is dynamic API deobfuscation, unpacking of 64-bit sample. And regarding static API deobfuscation, I packed with Domidar 2.3.5. It's commercial packer packed 32-bit malware. I downloaded it previously. The file. I made a sample code and packed with Domidar 2.3.5 with Tiger Red virtual machine. My tool is not well developed, so I need to type. I developed it using Intel pin to trace memory read, write, and execution. and I prepared the text file. In the text file, it contains the information of the analyzed packed file. It suggests some OEP or neo OEP, and the first column is the caller address, and the second column indicates whether it is call or jump and module, and the last one is the function name. So I used with this information only debugger script, and not that in 634 I use x634 debugger, and I translated it into x634 debugger script. So it can be done manually, but it can be done with debugging script. I use this debugger, but it is extremely slow and buggy, but I don't know whether there is a better debugger for 64-bit. I also use IDA Pro for debugging, but it crashes a lot when we analyze obfuscated binaries, so I used it. And here is the script. And we can run script. It has some bug, so it takes very, very long time. This is a simple example. Just pop up some message box. So this is the unpacking of a 64-bit sample, and for static API deobfuscation, I downloaded a file from VirusTotal 5 days ago. It is a lengthy binary malware that is doing some bad things. It is packed with emitter and generates some draw files and make some images and doing bad things. Some system services and shell commands doing bad things. So the name is foo428.exe. It took minutes, so I also prepared already. Oh, it's still running. Sorry, the font is too small. The script itself is similar to x634 debugger. I used some plugins, only debugger plugins called ODBG script, and for evade anti-debugging, I used Phantom and Strong OD and made some configuration, and I changed the configuration file of VMware Fusion in this machine to avoid VM detection. So it tells us what is the OEP and IAT start and the size of IAT, clear breakpoints, and get some information on module, and to resolve each API calls at the specified addresses. So the malware is loaded into OLED Burger, and it is packed, so we need to deobfuscate it by the script generated. And you can see in the address table, it is changed and the address is resolved. And when we search for wait a moment. All intermodular calls. Now we see that my tool is not perfect, so some calls are not resolved, but most of the API calls are resolved. And I found that some calls are not. When you dump this file with execution dumper, I use sealer to dump the file, and it can be dumped by entering OEP and IAT address and size. So we check the OEP. And IAT address and size. Then we do get imports and dump it. It's a normal process to dump. So here is dumped file. Although it is not perfectly deobfuscated, its import table is recovered, and we can check the files, and even we can decompile it. There are some errors, so we need to manually correct this unresolved addresses. So this is my demo. And how I implemented it is I use pin tool to resolve API addresses. It is developed under Windows 8.17, 32 and 60-bit on VMware. I used Visual Studio 2013 Intel Pin 2.14, the latest version, and use Python script to patch obfuscated call, and use reversing tools x64 debug, Oli debugger, and IDA Pro. The deobfuscation process is as follows. API resolver, that is a pin tool, get API information and generate a text file. And API information in the text file is used by a Python script. It's debugger script generator. So it produces debugger script, and when we debug the binary with debugger script and the packed binary, then we can get the obfuscated file. And when you dump the file, then we can do static analysis with IDA Pro. I showed the text file and the obfuscation script. So to wrap up, I suggested two API deobfuscation methods. One is memory access analysis for dynamic obfuscation. One is iterative run until API method for static obfuscation. And as a result, a commercial packer protected binary can be analyzed using API Deobfuscator, using debugger and disassembler and compiler. But it has some limitations. It is depending on dynamic binary instrumentation tools using, I use PIN. I also tested with Dynamo Rio, but the behavior is almost the same. But some packers can detect dynamic binary instrumentation tools. There was a talk in Black Hat last year, maybe, defeating the transparency feature of dynamic binary instrumentation tools. And the latest version of Obsidian detect Intel pin as a debugger. So in this case, I used Oli debugger to evade such things. It also delete hardware breakpoints. So I need some patient job doing breakpoints that cannot be detected, setting breakpoint, hardware breakpoint on some NTDLL files. And DBI tools crash in some applications. For example, when I try to analyze some game hacking program, then maybe game programs use some weird applications and they also have some protection mechanisms. So they cheat the pin itself. So DBI tool crash in some applications, and I don't know why it is crashed so far. So in such cases, I use also debugger and manually do some jobs. We can set breakpoint on memory read and write at some point and manually log or develop some custom script to unpack such files. But it takes too long. The API Deobfuscator I developed require 3 or 4 minutes with large files, but when I use such debugger script, it took about hours to deobfuscate the special packed application. But it works with debuggers. So as a future work, I wanted to develop emulator just for unpacking. Currently I have some emulator that is some extraction of box and some extraction of X32 EMU developed by Chris Eagle. And it is working, but it is a little bit tricky because they doesn't support the multi-thread when I extracted the CPU only. Yesterday, Unicorn, I heard a talk who developed Unicorn. There is a Dream, they says the Dream emulator, but it doesn't support multi-threading, so we cannot apply that in this case because Domidar use near around 20 threads to check whether it is analyzed or not. So I need some multi-thread support emulator. And for API call resolution, code optimization and binary diffing for static whole function obfuscation. And sometimes for custom packers use some weird obfuscation, so I need code obfuscator only for deobfuscating binaries. And I need backward dependence analysis for custom packers. And that's all. Any questions? Then, thank you. If you have any question, email me.